can change the slides and the pointer. Let me just. Hello, welcome back, everybody. Now we restart our section, plenary section. We have now Professor Janos Bergou from Department of Physics and Astronomy, Hunter College, and Graduate Center of the City, University, New York, United States. Thank you, Professor.
Thank you for the introduction. It's nice to be here, of course, and I'd like to thank Wanderlei for putting together this wonderful meeting and giving me the opportunity to see San Carlos for the first time. Also Luis Davidovich, my other great friend, who is personally responsible for my being here, and also our chair for not abusing my name too badly. It's a simple work on broadcasting quantum states in a network. It's a collaborative effort. I always run out of time at the end of my talk, so I'd like to introduce the crew at the beginning. The first two authors are from Stony Brook. The next two authors are Duff Fields, who was my graduate student and a brief postdoc, and now he's with the Army Research Lab with Vladimir Malinovsky there. And Mark Hillary and myself are from Hunter College of the City University of New York, longtime friends and collaborators. So this is the crew, and I hope the title is provocative enough, because there is a no broadcasting theorem, which says that quantum states cannot be broadcasted to more than one receivers. And of course, that's exactly what we try to get around here. So we will try to show that, yes, we can broadcast quantum states to more than one receiver. There could be more than one sender, and I will show a few protocols for doing that. Of course, we all know how to transport a quantum state to a remote party. There is teleportation. We all know about that. And I will review teleportation on one slide, because it is a kind of a benchmark. And please focus on the costs of teleportation. There are three costs involved. One is the entanglement cost. How much entanglement we need to teleport a state. The other is the measurement complexity. In order to do full teleportation, you need to do the full Bell measurement, which is a difficult thing to do. It cannot be done for linear optical means, for example. You need some nonlinearity for that. And finally, the communication cost is also rather high. You have to tell the result of the remote party of your measurement. So it could be one of the four Bell states. And this will be the benchmark to which I'm comparing all the protocols that I will be talking about. The scenario that I will be looking at is remote state preparation, which is simpler than teleportation. For example, no Bell measurement is involved, and it is less costly in many other aspects. So I will be focusing on that. Let me provide you with the one-slide summary of teleportation. It starts with Alice, the sender, and Bob, the receiver, sharing an entangled pair of qubits, one of the four Bell states. Typically, in most experiments, it is the singlet state. And then Alice is receiving a system, a qubit system in some unknown state. And her task is to transfer this state to Bob. And here is what she can do. She measures the qubit she has, the entangled qubit with Bob, and the qubit she just received in the Bell basis. And of course, the outcome of the measurement can be one of the 4 Bell states. She communicates the outcome to Bob, and Bob, depending on the outcome, performs one of 4 known unitaries. And miraculously, the qubit in his possession will then be in the state that was given to Alice. Now, let's look at the cost. It requires 1 entangled pair, so the entanglement entropy is 1 for this, or we can say it's 1 E-bit. The communication cost, classical communication cost, is 2 bits because Alice has to tell the result of the Bell measurement, so it can be one of 4 outcomes, one of the 4 Bell states. So the communication cost is 2 bits. Okay, so keeping that in mind, oh boy, what happened here? Can you, thank you. Okay, let's look at an alternative. It's the so-called remote state preparation. It's an extremely simple idea, and for simplicity, I will show it on the example of this so-called equatorial state. If you represent these states on the Bloch sphere, they are on the equator of the Bloch sphere. So it starts out with Alice and Bob sharing an entangled pair of qubits in the singlet state. And since the singlet is the same in any basis, all that Alice has to do is to do a measurement in the plus-minus theta basis. So plus-minus refers to this sign here, and those are orthogonal states, can be used as a basis, and tells Bob the result. Now, if she finds theta, the minus theta state, Bob's state is the plus theta. So they don't have to do anything else after this. Bob has the desired state, and if she finds the plus theta state, Bob needs a unitary rotation of the qubit he has, and he winds up with the plus theta state. So it's an extremely simple protocol. There is no Bell measurement involved. Alice just does a projective measurement on the qubit she has. The entanglement cost is still the same as for the teleportation because they need an entangled pair, possibly in the singlet state. So the entanglement cost is 1 E-bit, or 1, the entanglement entropy is 1. The classical communication is less than for teleportation because Alice just has to communicate one of the 2 possible results. And the measurement complexity is, of course, reduced tremendously because there is no Bell measurement involved. Alice does a local measurement on the qubit she has. So this is the basis for the rest of the talk, setting the scenario. So let's now look at an extension of this. Alice wants to send this equatorial state, the plus theta, to 2 parties, Bob and Charlie. Of course, the method, the most common method would be teleportation. Teleportation would require that Alice separately has an entangled pair of qubits with Bob and another entangled pair of qubits with Charlie. So the teleportation cost would be 2 E-bits, or the entanglement entropy would be 2, and 4 bits of classical communication, because separately she has to communicate she has to do 2 Bell measurements on the 2 entangled qubits she has and communicate the outcome, altogether 16 possible outcomes. So that would be quite high. The remote state preparation that we had on the previous slide would be somewhat simpler. It would still cost 2 EBITs, but just local measurement on the qubit that Alice has. And of course, she has to communicate the 2 times 2 outcomes to Bob and Charlie, so the communication cost would be 2 bits. All nice and dandy. Let's look at an approach which has even less cost in terms of entanglement entropy, and communication. So let's come to that. She will start with the 2 qubits prepared in the plus theta states, both, and these are the qubits that Bob and Charlie will receive at the end of the protocol, and entangles them with a Q-treat, not with other qubits, but with a Q-treat. So the index A refers to Alice. So Alice has a Q-treat. The basis vectors are the 0, the 1, and the 2. It's a 3-dimensional object. And she prepares this kind of entanglement between her Q-treat and the B and C qubits. And then, after the entanglement is done, and I will come back to that, how to prepare this kind of entanglement in a couple of slides later, she sends the qubit to Bob, qubit B to Bob, and qubit C to Charlie. There is a lot of entanglement here. Alice is now entangled to Bob and Charlie, and there is entanglement between Bob and Charlie also. Still, the entanglement cost is less than for teleportation or remote state preparation. So let's see what happens. Now, Alice decides on the value of theta. Well, let me come back here. Up to this point, there's no mention of theta in this preparation. So we don't see theta here. After the entanglement is established and the qubits are distributed, at any time later, Alice can decide on the value of theta that she wants to transmit to Bob and Charlie. So what she wants is she applies a unitary on the Q-treat she has in her possession, which is a very simple unitary. It imprints a phase on the 0, the opposite to 1, and nothing to 2. And then she measures in this fancy basis. You can check easily that this is indeed a basis, all normalized and orthogonal among themselves. So she measures in this basis. But this is a local measurement. She does a projective measurement on the Q-treat she has. No Bell measurement, nothing like that. A simple projective measurement on a Q-treat. And if she gets the first outcome, U0, Bob and Charlie will have the desired state. Now, if she gets U1, this one, then it is different than the desired state. There is an extra phase factor of pi over 3 here and pi over 3 there, but that can be easily corrected by this unitary transformation. So after this correcting unitary, they will have the desired state. And then if she gets the third outcome, U2, then Bob and Charlie have to perform the inverse of this unitary, U minus 1, and then they get the desired state. So the bottom line is that after a correction step, in all 3 cases, in all 3 outcomes, Bob and Charlie will end up with the desired state. I will come back to the costs. We will talk about that. But at some point, when I gave a preliminary version of this talk, somebody asked me, is it a strong restriction that Alice wants to send equatorial states? And it's not. The same thing works for arbitrary qubit states, not just for the equatorial states. So Alice can communicate a general qubit state to Bob and Charlie. How? Well, she prepares 2 qubits in this state and then entangles them with the qubit that she has, and then she will have this 3-particle entangled state, the qubit she has and the 2 qubits. And after the entanglement, she still sends the qubits to Bob and Charlie. And now she does perform the same unitary as before to imprint the value of theta to the qubits, and then does the same measurement as before in this fancy basis. And then after the measurement outcome, Bob and Charlie, if the measurement outcome is U0, the first basis state, Bob and Charlie will have the desired state. And if it's U1, there is this extra phase factor that can be easily taken care of with this unitary, correcting unitary. And if U2, then the inverse of this unitary will correct the outcome. And in all 3 cases, Bob and Charlie will have the desired state. So the point here is that the entanglement and the distribution of the qubits can be done at some stage. And then any time later, when the need arises, Alice can send the phase information to Bob and Charlie using this unitary and the measurement. So it's very easy to calculate the entanglement entropy for this scenario. And here it is as a function of this alpha absolute square, which is the alpha is the amplitude of the 0 state in the qubit, in this general qubit state. So what we see is it's a typical binary entropy function. Its maximum is when p is 1/2, of course, and the maximum is 1.5 or 3/2. So it's much less than teleportation, where we need 2 entangled pairs, and the each one has entanglement entropy of 1. So the total entropy is 2. For this, it's 1.5, which is a big reduction. Now, one slide, maybe 2, about how to establish the entanglement that we need, this 3-party entanglement between the qubit that Alice has and the 2 qubits that Bob and Charlie will end up with. And the heart of the scheme is this controlled V gates. V is the backshift gate. A very simple, V is a unitary, backshift unitary. It just transforms one basis vector into another one with this prescription. So the subtraction is modulo 3, of course, which means that the 0 becomes the 2, the 1 becomes the 0, and the 2 becomes the 1. So it just permutes the basis vectors. And the interesting part is here that the upper line is the qubit that Alice has. So this is a general initial state. The qubit is in the 0 state, and the 2 qubits are both in this alpha 0 plus beta 1 general state. The controls are the qubits, and the target is the qubit. So that's the main feature of this protocol. And if you look at what happens, it's very easy to see that this initial state, so the qubit is in this fiducial 0 state, and the 2 qubits are in this general alpha-beta state, both of them. Run this circuit, and out comes the desired entangled state that we need. So this is how to establish the entanglement that we need for this scenario. And I'd like to say that in all of the cases here, Bob and Charlie will end up with the desired state, theta. So the phase information is sent to them. Of course, the same result could be achieved by teleportation, but teleportation would require much more resources. So let me compare it to that. The entanglement entropy, we have seen that it is at most 3/2, 1.5 EBITs, not 2 as for teleportation. And if alpha or beta is less than the, so it's biased, then it's less entanglement entropy. The classical communication cost is reduced quite a bit, actually logarithmically. The classical communication cost is log 3 bits because both Bob and Charlie get the same message at the end of the measurement. There is no projection on Bell states. Alice just performs a local measurement on her Q-trit, and it's a projective measurement. So if you compare this to teleportation, you see that there is quite a bit of gain in all counts here. The protocol can be extended to n receivers from 2, so not just Bob and Charlie, but it could be Bob 1, Bob 2, Bob n, any number of receivers. It is still much more efficient than teleportation. For example, teleportation would require n Bell measurements and sharing n entangled qubit pairs. So the entanglement cost is n e-bits, and the classical communication cost is 2n bits. In this case, well, we need a qubit to begin with n plus, where d is n plus 1. But then the entanglement cost scales logarithmically with the size of the qubit, and the communication cost also scales logarithmically. So there is a lot of gain there, and of course, ultimately, there is only a local projective measurement on the qubit. All right, so far we discussed deterministic protocols. Let me show you some probabilistic protocols based on the same idea. It starts out with the same entangled state. So in this case, Alice wants to send an unknown phase, maybe unknown to her, to Bob and Charlie. So she establishes this entanglement that we always start with, sends the qubits B to Bob, qubit C to Charlie, and then she receives a Q-trit which carries the phase information. It's in this state at the bottom of the slide, but she may not know the value of the phase, theta. What she does is she sends, so she now has 2 Q-trits. Let me come back here. The first Q-trit is Q-trit A with the 0, 1, and 2 bases. The second Q-trit is the Q-trit D, also with the 0, 1, and 2 basis vectors. So what she does is, help. Same thing happened again. What she does, thank you. She sends the 2 Q-trits she has into a C-shift gate. So the C-shift gate is explained here. Essentially, it's the upshift unitary, again, just permuting the basis vectors of the Q-trit, conditioned on the state of the first qubit. So the state of the D qubit is shifted by either one step or two steps or no steps, depending on what the state of the A qubit is. So if A is 0, nothing happens. If A is 1, it is shifted by 1. And if A is in the 2 state, then D is shifted by 2. And then Alice measures the qubit D. Again, a local measurement, no measurement in the Bell basis. In the computational basis, 0, 1, or 2. And if she gets 0, Bob and Charlie will have the phase information imprinted on their qubits. However, if she gets the other two outcomes, U1 or U2, they cannot perform the correcting unitary because the value of the phase is unknown to Alice, and of course it's unknown also to Bob and Charlie. So in those cases, they just discard the results, and this is then a probabilistic protocol. It succeeds with probability 1/3 and fails with probability 2/3. But when it succeeds, the unknown phase information is transferred to Bob and Charlie. It can be extended to more than one sender, A1 and A2, on the sending side here with a very similar entanglement, but now between two qubits, A and A prime, and then the two qubits B and C for Bob and Charlie. After this entanglement is established, the qubits are sent to Bob and Charlie, and separately A1, Alice 1 performs this unitary with maybe one phase, and Alice 2 performs the same unitary but with a different phase, theta 2, and they do the measurement as before, and then it turns out that Bob and Charlie now receive this state with a phase imprinted, but this phase is jointly controlled by Alice 1 and Alice 2. It is always possible to add more senders and more receivers. It can be extended in many of these directions. How much time I have? 5 minutes? 10. Okay, good. And also other variations. One can send different states to Bob and Charlie. One can have one state in one basis, say the computational basis 0, 1, and the other state for Charlie in the X plus minus basis. So there are all kinds of variations of this. Another is that they can extend it to sending qubits instead of qubits to Bob and Charlie with some extra phase information in it. All kind of extensions that you can dream of. Let me show you a very simple application of all these ideas. It's quantum voting. Bob and Charlie are the people who vote in this scheme, and Alice is the person who counts the votes. Okay? All of them are considered honest, although authentication can be built into the scheme, so it's not really a very strict requirement. And of course, an eavesdropper would like to figure out how Bob and Charlie voted. Okay? So Alice starts broadcasting several states to Bob and Charlie, all of this form, but possibly with different phase angles in them. And then Alice announces the values of the angle for some of the qubits, and Bob and Charlie then measure those qubits in the plus minus theta basis in order to verify that it has not been disturbed. If there is an eavesdropper, then in some measurement cases, they will end up with the orthogonal state, the state that was not sent. if in all cases they find the state that was sent, they can be sure that there is no eavesdropper. Okay? And after this, if the channel is authenticated, they vote. How do they vote? If they vote yes, they do nothing. They send back the qubit to Alice that they had, and if they want to vote no, they apply the sigma z transformation on the qubit they had, so it turns it to the minus theta state, the orthogonal state. So they send back the qubits to Alice, who measures them in the plus minus theta basis. And if she finds the plus theta outcome, she knows that they voted yes. If she finds the minus theta outcome, she knows that they voted no. Okay? So this is a relatively secure way of voting in the quantum way, which is provably secure against eavesdropping. And to be sure, they can do this with several qubits, increasing the probability that there is no eavesdropper at all. Okay, so this is one interesting application. Another one is communication between Bob and Charlie. They can send an unknown phase among themselves, imprinting the unknown phase on Bob's qubit, for example, and sending that to Charlie, who after this entanglement and measurement ends up with the phase state phi, the one that Bob wanted to send him. So these are two applications. There are other fancier ones. One is establishing gates. In this case, it's the SU2 rotations. In this case, it is the C0 gate. And this is for measurement-based quantum computation, establishing one of the required distributed entanglement states there. But I'm not going into details of that, but this is possible with repeated application of this simple scenario. This is just the scheme for that. Now, up to this point, everything was fine and dandy. We assumed that we have entanglement, we have everything perfect, it all works well. But if we are in a network, then we have to worry a little bit about how entanglement propagates in that network. And here are some recent results about that. For example, let's look at the entanglement swapping protocol of DCLZ, Duan, Lukin, Duan, Sirac, Lukin, and Zoller, where in order to establish entanglement between the beginning and the end of the network, we need to have 3 entangled qubit pairs. One between Alice and Bob, the first 2 people in the network, then one between, say, Charlie and Dave, next 2, and then between E and F. So 3 pairs of entangled qubits. Then the protocol works in such a way that from the AB pair, we take 1 qubit in Bob's possession, and from the CD pair, we take 1 qubit in Charlie's possession. And we project it on the Bell state, so we do a Bell measurement on those 2 qubits. And depending on the outcome, there is entanglement between A and D, and then we do the same between D and E, measuring the Bell basis, and then depending on the outcome, there will be ultimate entanglement between E and F, the first and the last in the network. And the question is how the average concurrence changes in this protocol. And here is a simple result. The average concurrence between A and F is the product of the individual concurrences. You can think of this as an upper limit. So if there is any imperfection, it is less than this. In the ideal case, it is at most this much. So let's look at the somewhat non-ideal case. We have an entangled pair of states, but there is some noise added to it. So we have a mixed state. The concurrence is either 0 or this first expression, depending if it's larger than or less than 0. Okay, so if the input state is of the form that we had on the previous slide, so this mixed state, we see that depending on how much noise we add to the state, if it's too much, P is the probability of adding the noise. There is no entanglement at all in the state. So there is a boundary in P below which we have still entanglement, above which there is 0. And the maximum is at P equal 2/3. So if P is larger than 2/3 in that mixed state, there is no entanglement at all. Now, let's use this mixed state twice in the entanglement swapping, and we see that in the ultimate, at the end of the network, the region where we have entanglement is even further reduced. So now you see that P has to be actually less than 0.5, going down from 2/3 to 0.5. If we apply it one more time, again it is reduced, and so on. So one has to be very careful when we say something about the propagation of entanglement. If we have qubits, n-dimensional object, then the boundary for the noise is given by this expression. So if n is 2 qubits, then 1 minus 1/3 is the 2/3 boundary. And if n is larger than that, then the boundary actually increases with the dimensionality of the qubit. And for the output, the P is reduced. We have n plus 1 here and square root of n plus 1 here. So clearly, we have a smaller region where we have entanglement than for the input. And it's easy to follow this. If the entanglement of one state is this 4 times lambda 0, lambda 1 in the Schmidt decomposition, and P is the amount of noise, we see that the average entanglement after just one swap is given by this expression. So it's reduced by this factor. Now, if P is not too large, we can approximate this expression for n entanglement swapping with the exponential, which means that the entanglement degrades exponentially with the length of the network. So one has to be very careful when we apply this for a network situation. And maybe one more remark here. I'm not going into any details. If we have a linear optical network, we cannot resolve all 4 Bell states in this linear optical network. At best, we can resolve 2, but most of the times only 1. So with linear optical network, propagation of entanglement is impossible. Perfect propagation of entanglement is impossible, and one needs some kind of nonlinearity there. So with that, I'm coming to the end of the talk. The 2 scenarios that we had here with more details were published in these papers, and then what we can do with bell-like states, how to discriminate with linear optics was studied in here, and how the average concurrence propagates in a network using entanglement swapping was done in this work. And with this, I thank you for the attention.
Thank you very much, Janos, for the nice talk. Now we still have time for a few questions. Okay.
Janos, thank you very much for the nice talk. I would like to know whether this Q-treat could be encoded on the same particle as one of the qubits. So could actually our physical resource be 2 particles and 2 degrees of freedom of one of them?
So if I understand the question well, you're asking me whether you can use a multi-level system where some of the levels would serve as the qubit and the other levels as the qubit, right? I think that's possible. Typically, there are 2 ways of extending a Hilbert space. One is the tensor product way, and that actually implies that you have separate particles for each system. And the other is the direct sum way, where you use some of the unused degrees of freedom for the other purposes. So 2 degrees of freedom, 2 levels could be used as the qubit, and if it's a multi-level system, the other levels could be used as the qubit. Yes, it's possible.
Okay.
Thank you. In quantum computing architectures, recently there has been a lot of emphasis on this modular architecture, where you have sort of smaller qubit systems, and then you connect them with a quantum channel. Based on these results, I'm thinking you would be skeptical of those architectures.
I'm a little skeptical, yes, absolutely. I think this was based on a very careful analysis of looking at what really happens in a network. And of course, we all know that no noise is, well, it's a theoretical something. But if you are an experimentalist, then my experimentalist colleagues, Ephraim, for example, taught me that there's always noise. Whatever you do, there is always noise. You cannot avoid that. And I was looking at a simple scenario to estimate what it does to the entanglement. And as we see, over a long network, inevitably, the entanglement will be degraded. Thank you. So we are in agreement. I'm glad.
Okay, one more question. If not, let's thank Janos again.
Thank you.
Cid está ali em cima.
Hey, it's a check in your pocket if you lost a hotel card. If you don't find in your pocket, it's here. Okay, I don't know what hotel it is. Sleep Inn or... Yo, what's the hotel? Yeah. Everybody understood? Check your pocket. Thank you. Ô Cid, tenta falar dali, pô. Você quer falar com o microfone? Eu prefiro. Mas procura não ficar com a mão assim, porque quem está assistindo no YouTube falou que o som vai e vem, vai e vem.
Okay, your next speaker is Professor Cid Araújo from Universidade Federal of Pernambuco. Thank you very much, Professor. Let's start then.
Well, thank you very much for the introduction. Thank you, Vanderlei, for the invitation to present this talk here. I'm from Recife. There, it's about 2.5 kilometers from here. Recife is in the coast. It's a big city with about 2 million inhabitants. And my university, it is a young university with about 40,000 students. And in my lab, we have these two main research lines. We have been working with these random lasers and some nonlinear spectroscopy with the metal dielectric nanocomposites, colloids with metal particles. So today I'm going to talk about these random lasers. So the outline of the talk is the following. I will make a short introduction to random lasers, saying the main characteristics, how to obtain it to operating. I'm going to talk a little bit about the influence of nonlinear susceptibilities and present some applications, very few. And then I come to the subject of the talk, which is first the glass behavior of light. Second, replica symmetry breaking, and then I will close with some remarks. So the story of random lasers started a long time ago in 1966. It was in Soviet Union. These people here includes Bazov, who was a Nobel Prize winner. What they did, they operate one laser without mirrors. Just they put some scatter in one position of the mirror, and then they operate the laser. Letokov did some more experiments with that, and during a long period, which goes from 67 to the 90s, most of the work was done in Soviet Union. In this book here, you can see a lot of examples of this kind of research done mainly in Soviet Union. The first efficient random laser was developed in Brown University. It was based on a colloid with rhodamine in alcohol. And what they observed there was that by adding some particles in this colloid, they got a very large increase in the luminescence of that cell. And what they observed was a reduction of the line width just due to the presence of these titanium dioxide nanoparticles. The reduction of the line width is, at the same time, there is a very large increase in the intensity of emitted from this colloid, and the behavior of this of the emission shows a kind of threshold, like in conventional laser. So that was the story of the first efficient laser. Few years after that, she developed a laser based on a semiconductor. And in that case, she observed that besides a smooth spectrum, the laser, the random laser, the system emits some spikes. And those spikes were identified as a presence of some closed loops inside the powder that she used. So from that time to now, there is a convention that we may have these two kinds of random lasers. One which is called the incoherent random laser, which is based only on amplified spontaneous emission, and this one which is the coherent one, where the spikes are present. So there are kind of constructive interference inside the active medium. This system behaves like a real laser, although there is no mirrors. They measure the photon statistics. They observe Poisson distribution above threshold. So that's a kind of laser without mirrors, and that's not a new things because you know that there are many astrophysical lasers. So we can operate lasers of different types. For example, like in the rhodamine titanium dioxide, we may have the scatters inside the gain medium. We may have scatters being the laser emitters, like in the zinc oxide laser that I mentioned. Or you can combine some nanocrystals with ions, luminescent ions, and some particles, for example, to get enhancement of the luminescence. So the multiple light scattering is the essential phenomenon. So instead of mirrors, these scatters, the particles, nanoparticles or microparticles, they behave like mirrors. And so you can have this emission with these spikes, which corresponds to a kind of optical cavities, just because of the closed loops like there. So you have some interference, constructive interference. Then you have this select wavelength. So you have a kind of cavities and spectral modes. So there is no optical cavity, external optical cavity, but there are optical modes due to the scattering. So there are several differences between conventional lasers and random lasers, like you see here. I would say that for conventional lasers, one problem is that the speckle. Speckle is quite complicated if you are going to make images, for example. In random lasers, you can control the speckle. Speckle are due to the coherence, spatial coherence and the temporal coherence, so you can control it. However, the light is emitted in all directions. You just shine a beam, a laser in a sample, and then you have this emission in several directions. At the beginning, they called this photon bomb in the 60s. So speckle can be controlled. We have no directionality. We have short coherence time, small spatial coherence, etc., etc. So the first random fiber laser was developed in 2007. What we did was we took a microstructure fiber, and we put inside the nucleus of this fiber, we put the colloid, which was used in 1994 to operate the efficient laser. So we observed this reduction of the line width, we observed this threshold behavior, and the system was much more efficient than the conventional laser based on a cell. So after this, we solved one problem, that we have directionality for the laser, although there is no optical cavity. And there are several schemes now that you can use for these random lasers. We can use a scheme like this, where you focus the beam inside the cell and then you measure the emission. You can put a kind of optical cavity or optical waveguide. We can use films, or you can put in a real fiber with some luminescent ions. For example, erbium ions, rare earth ions. So we have been playing with these kind of different schemes. And I'll give you here one example of how interesting is this system. In this case, we have these nanocrystals doped with neodymium. We excite neodymium in resonance 800.06, and you know that there is a neodymium laser at 1.06. We have a powder, and then we shine laser in the powder, and then we analyze the laser, the emission. The spectrum here shows the spectrum at low pump, low excitation intensity, and the one which is narrow is obtained by increasing the intensity of the pump laser in such a way that we have these characteristics of a laser: reduction of the line width and a threshold very well defined. With this, we decided to study different kind of phenomena. So we can observe, besides the stimulated emission and multiple light scattering, we could show some effects of nonlinear optics that I'm going to describe now. So the first effect which was observed was this self-frequency conversion. So this is a laser that emits at 1.06 when we pump with 806. That's the laser, the random laser. However, the intensity is so large, then this laser may combine with the pump beam, and then we got emission in the blue. Or we may get second harmonic of the random laser. Or you may get a second harmonic of the pump beam. So it's a multi-wavelength laser with a narrow line width. Based on this, we could operate a tunable random laser, just changing the concentration, looking for the correct, good concentration of neodymium, and pumping with different wavelengths. We could use this tunable laser, tunable in this whole spectrum here, which goes from the green to the violet. So it's a laser where you have a Chi2 effect, important susceptibility, and then you can combine some frequency and second harmonic in order to have it tunable. A little more that you can do with that. Just by increasing the concentration of neodymium, the ions of neodymium start filling different positions in the crystalline structure. And because of this, we may have emission in two different wavelengths. Wavelengths at 1.06 and another one which is less efficient in different sites of the neodymium. And what we observed was that just by changing the temperature, we could get a kind of thermometer. Just by changing the temperature, we change the ratio between the two emissions, and then we could have a thermometer, which is a thing which is now of very large interest in the literature, of this optical thermometer based on these nanocrystals. Besides this second order susceptibility, we may have Chi3 is present because we have some large intensity, but we may have also evidence for Chi5, Chi7, etc. And then we could explore this just by playing with different kind of lasers that I'm not going to detail here because of time. But we could observe fifth order nonlinearity contribution of these random lasers, and we could observe that this fifth order nonlinearity influence the statistics of fluctuations in the above the threshold. So these nonlinear susceptibilities, they contribute for interaction between the modes. So we have a kind of a laser which emits different wavelengths, and there is a correlation between the different wavelengths because of this interaction, because of this susceptibility. So that's a random laser. It's ease of fabrication, very easy. Large spectral irradiance. You can paint a surface in order to have a laser. And you can operate it as a continuous wave, pulsed laser. We can operate to obtain Stokes emission or anti-Stokes. In the case of anti-Stokes, you play with, we have different examples of excitation by multi-photon absorption. 3-photon absorption in zinc oxide, for example, can produce a random laser in the UV with very low threshold. So that's the material, that's the system that I'm interested here in this talk. Some application by other groups that are more recent, people have been using trying to excite these lasers just by using electric current. These people here, they obtained kilowatt random fiber laser. There is 2 or 3 papers in the literature where people speculate on the possibility of using this random laser to do fusion experiments. The motivation is because since there is no speckle, you can focus the beam in one very small region. While if you use a conventional laser, because of speckle, when you try to focus the beam, you have several different places where the laser is focused. So the efficiency of fusion could be larger, but that's this. I put here the phrase of this author here that it's careful, but it's promise. Okay, and several other applications. For example, these people in Canada, Raman, Kashyap, they operate the random laser as a generator of random numbers. So many different applications for this right now. Okay, so now I'm going to talk about this glassy behavior of light. So we want to identify a system which is analogous to our laser, and where people use the statistical mechanics ideas in order to explain the behavior. So these people in Italy, they published this paper in 2006. And the idea is to have analogy, to exploit analogy with magnetic systems. I don't know if you are familiar with the magnetic system, so I introduce a short course on spin glass. But before that, I want to say that there is a strong correlation with this idea of glass behavior of light with the subject of the random laser of the Nobel Prize of 2021. That was the citation of Jorio Paris for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to the planetary scale. And that's the idea of replica symmetry breaking that I'm going to try to present here, although I'm not going to be very deep on the ideas. So with the random lasers, people were able to provide the first evidence favorable to this theory. This theory has been used since a long time for the statistical mechanics people, but there was no direct evidence of this idea. With the random laser was the first time that we can show it exactly. So what is a spin glass? You probably remember that paramagnetic material, we have no magnetization. You may have ferromagnetic materials or anti-ferromagnetic materials that can be described by this Hamiltonian. In this Hamiltonian, when this coupling constant, that's called exchange integral. When it's positive, then you have a ferromagnet. When it's negative, you have an anti-ferromagnet. And it depends, the signal depends on the overlap between the wave functions of these several atoms. But in some cases, instead of have this kind of order, you may have a kind of this spin glass. So there is no crystalline order for the spins. For example, if you have a positive J between these 2 points, and you put a spin here, they will be aligned like that. But if the J is negative with respect to this point, and positive with respect to this point, there will be no way for this spin to be like in that position. So it could be up or down, and so it becomes a kind of frustration. There is a disorder, and then you have a frustration. And because of that, you may have the ground state, you may have several potential wells. And there will be a distribution of probability for different values of J, positive or negative. So frustration and disorder are essential mechanisms for this kind of system. And the way to study this kind of behavior is using this order parameter. Q relates the spin in one time with the spin in the same position in another time. That's called replicas, because the system, you have some statistical fluctuations, thermodynamic fluctuations. So the ground state could be with the spin up, or in the same position spin down, and another one spin to compensate for that. So you can describe a spin glass by this distribution of replicas. Replicas corresponds to a particular position of the spins. And then what we say is that the systems are identical. Under identical conditions, they may have fluctuations. And so the replicas, which should be equal, like in quantum mechanics without fluctuations, here they may have a different behavior. The system may evolve in different ways, although the potential, external potential is the same. So for the students, that's a counter example of the evolution in quantum mechanics curves, okay? Just because of the fluctuations. So in the case of random laser, we may find something that is analogous to that. For example, suppose that you are with a pulsed laser. Each pulse of the laser may excite a different spectrum. The spectrum is a replica. And the different spectrum may have amplitudes, different amplitudes for different wavelengths. And so there is this kind of fluctuations, and there is a mode coupling because of the nonlinear susceptibilities. So we established these analogies between spin glass, magnetic material, and random lasers. Spins corresponds to modes of the field. Temperature corresponds to the inverse of intensity. Temperature is the control the phase transition of spin glass. So the intensity here produces a phase transition. What's the result of that? Because of the intensity, we change the intensity, and then we pass from a paramagnetic case to an ordered case. So we go beyond the threshold of the laser. So that's the intensity. So the first experiment was done by Italian group. They study organic system, and I'm going to give some details of this. So the idea was to analyze the fluctuations. So you take different spectra, and then we calculate this intensity, average intensity, and then we look for distances between the intensity corresponding to a particular replica, and then we calculate the order parameter like that. Here in the numerator, what you see is this kind of fluctuation difference between this replica alpha and the replica beta. So there is a competition between the optical modes. So there is different replicas. And the mode coupling via the nonlinear susceptibility. So the random laser 2D in one film was the first one which was presented in the literature. And the order parameter is like that, Q equal to 0 below threshold and equal to 1 above threshold. So that's one way to identify if you pass in the threshold of the laser. So besides to look for reduction of the line width and the change in the behavior of the emitted intensity, you can use also this order parameter in order to identify the threshold of the laser. And then you calculate this probability distribution of the replicas. For low intensity below the threshold, so you have it's set at 0. It means no correlation between the modes. But when you increase the pump power, then you see that the modes becomes correlated or anticorrelated. Q equal to 1 or minus 1. So that's a way which these people, they show that. We did almost the same time experiment with a 3D random laser. With a 3D random laser, we use the nanocrystals that I mentioned before with the second harmonic, some frequency, etc., because they are efficient. And then we did experiment and look for different spectra. And you see that for different positions of the intensity of the pump intensity with respect to the threshold, there is a change in the spectrum of the laser. So these fluctuations we take into account in order to calculate the order parameter. Okay? So that's the result of this 3D random laser, where we observe this. The statistics is made for 1,500 spectrum. 1,500 spectra or spectrum, I don't know. Okay, so you see that there is this possibility to have this 2D or 3D laser, or in a quasi one dimension. So in this case here, we use a random fiber laser with a grating marked inside the nucleus of the fiber. And then the system is quite simple because it's just a small piece of fiber with a diode laser pumping it in a continuous wave, and then you see the threshold behavior and the behavior of the intensity over there. And then we could study the fluctuations of the intensity. I take the average intensity, integrate for all wavelengths, and look for the fluctuation in the intensity. So above threshold, instead of to be a dependence of Gaussian statistics, we have these LPHYS statistics that you mentioned in your talk before, right? So that's another way to identify a threshold for a laser. Just look for the behavior of the fluctuations of intensity. Instead of having a behavior like a Gaussian statistic, you have a power dependency statistics, which is the LPHYS statistics. Okay, so we have been interacting with these people in Italy, so they did this theoretical work in here, where they study possibilities of different phases. I mean, what we studied before was a change of paramagnetic to spin-glass, analogous of that. But this diagram here, they propose other kind of phase transition. And then we look for that, and then we could observe a phase transition from para to ferro, equivalent to ferro. So that's a kind of spontaneous mode locking without any saturable absorber inside the cavity. Okay? So you see that this system is a very rich system to study. So I will not have time. I don't know exactly how I have. Want to tap? 10 minutes? Ah. Okay. When I prepared here, I thought I would not have time to go into details. But, well, our group at Recife, you heard of last Tuesday, Anderson Gomes, who is my department, my collaborator, he presents several new effects that we studied in this, with these random lasers. He mentioned all this in his talk, but it was so fast that I decided to put here the titles and say the idea. Okay? So we have been doing studies of Monte Carlo on these systems. We have interaction with some theoreticians in our lab. So we have this approach based on this random matrix theory. I was there, and I saw that watching the computer of someone over there, that he is working with this random matrix theory. I don't know random matrix theory, but our theoreticians, they know, and they made this that seems to be very powerful technique. And photonic Hall effect, an effect which is analogous of the magneto resistance, So it was identified. And here is a experiment done in collaboration with one colleague from Catholic University in Rio, Jean-Pierre. I think that he's around here, he's there. So they observe mode locked of random laser generated by transform-limited optical pulses, which is a little more than the mode locked that we observed a few years ago. So, as you can see, random lasers are complex systems. Complex system in the sense of statistical mechanics. So complex is not complicated. It's not complicated. Complex is in the way of statistics people look for that, is that you can have all these phenomena that results of fluctuations. So the number of experiments that we did shows that they are excellent platforms for the study of laser physics, nonlinear optics, statistical physics, nonlinear dynamics, and atomic physics. Because you remember that Tuesday, Anderson mentioned here that Robin Kaiser in France, he is doing this kind of random lasers in cold atoms vapors. So just to simulate the atmosphere of stars. And so I believe that we may find several different kind of phenomena to study if we exploit a little more this kind of system. And just for the students, if they want to read more, I want to suggest this reference. That's a kind of propaganda, right? But we wrote this paper, it was published in June or July 2021, where we did a very detailed of the literature. The paper has a 69-page, 443 reference. So if you want to enter in this subject, that's a good reference. But we did not include at that time what's called the flexible and stretchable random lasers. So in this review here, we have this discussion and examples of flexible and stretchable random lasers, which was written in 2022. And this year, last year, we published this book, which is a kind of a study of Levy statistics and spin-glass behavior in random laser, which for any student who is interested in entering this field, I think that we have this, I would say, updated reference up to that time. Okay? So I think that I'm finished now. We do not have a big laboratory, but I have an interaction with several friends. We have people, these people here are professors in our physics, in our university. So I have interaction with these people, with some students and postdocs, and some external collaboration with people from different places, from different institutions. So I think that Anderson could not show everything that he had, and I have time enough to talk. Okay, but then you have an idea what these random lasers are. Thank you very much for your attention.
Thank you, Professor Araújo. We still have plenty of time for questions. It's nice.
So what is the smallest wavelength at which random lasers
What's there?
smallest wavelength at which random lasers can work?
Oh, the smallest wavelength. Okay, we operated in the UV and violet by using these semiconductors, zinc oxide. You can have a emission in 380. I cannot tell you if we can operate in a smaller wavelength now. But if we have enough intensity, then we can double frequency. So maybe we can go for the smaller wavelength. It depends very much of the material that you use. Okay, you have to select a proper material for each range of frequency. So that's in our case, we go from 380 to about 1200 nanometers. So different materials and different schemes, fiber, colloids, different schemes.
So, those ceramic lasers that they start and then they sinterize, is that a good way to produce the material that I want in a controlled way for a random laser?
Yeah. I took out from the presentation exactly like that. We had now we are operating this kind of glass ceramic. Okay, you take a glass and then we make some treatment, thermal treatment. Then you nucleate small crystallites inside, and if you have at the beginning put some rare earth ions, for example, some of these rare earth ions may go inside the crystallites, and then you can operate a laser like that. And then we have two publications last year with this tellurite glass ceramic. So I can show you later. Yes, yeah, of course. Mm-hmm. Yeah.
Professor, sit here. So I see that this is like a different method that you can generate different frequencies based on a single frequency that you have available, for example, depending on your material. My question is that how stable is your peak frequency, and how if you have ways to tune this power, for example, based on the input power as like a feedback to control the...
Yeah. We do, there is a big difference between random lasers and conventional lasers, because you have several years to play with this conventional lasers, so the engineering there is much more advanced. Okay? So in our case, we did not play up to now with this feedback to control intensity. Okay? So we are studying just fluctuations of the laser. And the fluctuations, it depends very much on the way you excite the system. So if you work with a continuous wave excitation, so the laser is very good, very calm. But if you work with a nanosecond laser, so you may have fluctuations, very large fluctuations. But up to now, fluctuations were a thing that we desire, because we want to study all these things of replica symmetry breaking up to now. Okay.
More questions?
Sid, thanks for your talk. So I was curious, what is the beta factor for these lasers? Beta meaning the fraction of the spontaneous emission that participates in the lasing, right? So usually, I mean, you have this thresholdless regime where beta equals to 1, so the whole fraction of spontaneous emissions participates in the lasing regime, as opposed to beta equals 0, where none participates. And they call beta equal 1 thresholdless laser, because the threshold curve is smooth when beta equals to 1. And it looks like from one of the initial slides that you showed that the curve is rather smooth, right? You don't see this sharp transition in the light emitted versus pump-powered curves. So do you have numbers for that?
I would say that if you work with colloids, the transition is not sharp. It's not sharp just because even if you pump with a picosecond laser, the transition goes in almost, I would say, microsecond rise time. But if you work with rare earth, then it's more fast. That's incredible, because rare earth has a long lifetime. However, it works with things like nanosecond. Okay? If we pump with a picosecond, then we have behavior of nanosecond in the die. So I cannot tell you the limits up to now. Okay? But maybe next conference I can show.
Thank you. More questions? If not, let's thank Professor again.
Thank you very much.
Obrigada, sir. Obrigada. And now lunchtime.